Hi all. Today we discuss some examples connecting the operators what we have discussed in the previous classes. For the examples we need to review some references. F of x plus h can be written as f of x plus h by 1 factorial f dash x plus h square by 2 factorial f double dash x plus etc. So this is what we call the Taylor series expansion of f. You might have seen this in the previous classes. Otherwise, you just keep it in mind that this is the Taylor series expansion. Later, you will study this in the calculus class or the real analysis classes. So, for the time being, you just remember this. This is what we call Taylor series. Taylor series of the function f. Okay, so if f is a smooth function, then f of x plus h can be expressed as a series expansion like this. And we have seen in the previous classes that e raised to z can be written as 1 plus z by 1 factorial plus z square by 2 factorial plus etc. So that is the expansion of the Taylor series expansion of particular function e raised to z, or you can derive this equation from the above formula. By putting this f instead of this f, you can replace this f by e raised to x, then you will get this one. And log 1 plus x, this also came from this formula. Log 1 plus x equal to x minus x square by 2 plus x cube by 3, etc. And one thing you need to remember is d, the operator, the differential operator d by dx is denoted by capital letter D. Okay, so using this we need to prove some problems. First problem is we need to prove that capital D is nothing but 1 by h times the forward difference delta minus 1 by 2 delta square plus 1 by 3 delta cube minus. We need to prove this formula. That means this is the relation between differential operator and forward difference operator. Okay. For this we start with the shift operator E of f of x. This is defined as f of x plus h. Using the Taylor series expansion of f, you can replace this f of x plus h by f of x plus h by 1 factorial f dash x plus h square by 2 factorial times f double dash x plus etc. And you can replace this f dash x by d of f of x. So we write this is same as f of x plus h by 1 factorial df of x. Df of x is d by dx of f of x, that is f dash x here, plus h square by 2 factorial d square f of x plus etc. So this d square f of x is d square by dx square of f of x, that is the second derivative of f. Now you write this is equal to 1 plus hd by 1 factorial plus h square d square by 2 factorial plus etc. of f of x. When you apply this operator to this d, this f of x, you can get the first term as f of x, the second term will be h by 1 factorial times d of f of x, that is f dash x, and so on. Now you write this is, we compare this bracket with the expansion of e raised to z. So this is 1 plus hd by 1 factorial, this is hd whole square by 2 factorial plus etc. So this can be replaced as e to the power hd. Okay, this is an operator, in fact, it's an operator of applied on this f of x. Okay, so we know that capital E is equal to capital E of f of x equal to e hd of f of x. So this implies E is equal to e to the power hd. Okay, then by taking log on both sides, you can write this log E is equal to hd. Consequently, we have proved that E is equal to 1 plus delta. So log of 1 plus delta is equal to HD. Now you use the expansion of log 1 plus x. Okay. Instead of 1 plus x, we have 1 plus delta. So you need to replace all x's in this the right hand side of this equation by this delta. So you'll get a delta plus delta minus delta square by 2 plus delta square by 2 plus delta cube by 3 minus etc. is equal to HD. Now you can get D is equal to 1 by h times delta minus delta square by 2 plus delta cube by 3 minus etc. Okay, so this proves our required result. So this is the one example, and we will discuss another example as well. So that is the relation between delta forward difference and backward difference. The result is nothing but forward difference, backward difference. That is this composition of f of x. Prove that this is same as taking the difference between these two operators. Okay, we need to prove this result. There is another example. To prove this, we start with delta del of yn or f of x. Then this will be delta of this. One way of proving this is to evaluate this LHS and RHS on this yn independently. So this will be yn. This is delta del of del yn. That is delta of del yn is yn minus yn minus 1. And by distributing this delta, you can get the forward difference of yn, that is yn plus 1 minus yn, and minus of forward difference of this, that is minus of yn minus of minus yn minus 1, that is plus yn minus 1. So this is the LHS, and you find RHS. Delta minus del of this yn, you will get delta of yn. Delta of yn is yn plus 1 minus yn, and minus of del yn. Del yn is yn minus of minus, that's plus yn minus 1. So from these two equations, you can get easily write this delta del is same as delta minus del. This the other method is you can also prove this result using the formula that we have discussed in the previous class. So that is we write delta of del can be written as delta of this del can be replaced by 1 minus e to the power minus 1. We have already proved this result. This is a relation between del and e. So that is equal to this one, and we know that this is equal to a delta of 1, that is delta itself, and delta of e to the power minus 1, that is equal to delta minus del. We have already proved the relation between delta, del and e, as this quantity is nothing but del. So delta del is same as delta minus del. You can prove this the same result in this method also. So if the question is asked for 2 marks, then you can write this one. Otherwise, you can explicitly prove LHS and RHS. So this there are other examples discussed in the example side. So please go through it, and please try to work out all these worked out examples given the textbook. Okay, so later you will be asked to submit it for an assignment. Thank you.